Hello everyone, we'll start our session in next 5 minutes. Hello, everyone. So, today is the fourth live session. We are talking about multipath fading environment, and my name is Annu. I'm from IIT Hyderabad. So, today's session will be having these parts. First is understanding the causes and models of multipath fading. Then, second is derive and interpreted relay statistical characterization. Third is computing the BER under fading for common modulations. Fourth is distinguishing the narrow band and a wide band fading, which is relating to the coherence bandwidth or time. And fifth is characterize multipath channels like PDP, RMS delay spread, and Doppler. So finally, we will be talking in depth about this modulation and diversity choices for fading channels. So these are the topics which are taken from the Sir lecture slides, and then we will directly solve the problems related to week 4. So the point is like the signals propagate via multipaths due to, as we know, reflection. Reflection is nothing but it is a surface. Whatever surface it goes, it reflects. And second is refraction. Like if there are different layers, then it is called refraction. The third is diffraction. Like if it is edge, the point edge is there. Okay, then it is called a diffraction. And finally, the scattering, like that is a small objects. And I think if you may wonder what causes the multipath fading, like large scale fading or small scale fading, you should know that also. Like what exactly are the causes of these uh, fading effects? Then the point is like if each path introduces this delay, so you're having this transmitter, the receiver, so it is using the delay each path. That's why it is called multipath because of these reasons. So it what exactly it does, it has delay and the amplitude AI and the phase I. Three things are there. Okay. So the baseband signal received, which is a continuous time, is RT is equal to summation of I is equals to 1 to N AI S T minus tau I e power j phi I plus NT. So suppose you are having one signal, this A1, ST minus tau, the amplitude associated with the ST minus tau I is A1, and the phase associated with that the signal is e power j phi I. So if you sum it, and finally the received signal at this base one is this. This is the received signal, where NT is AWGN, and multipath causes. It causes either constructive or destructive interference, that is fading. Channel impulse response and tap delay model, the line model. So here we are having in 3GPP standard, we are having different channel impulse response. So discrete tap delay line white sense model is HT of tau I, T of tau, which is now it is also a function of tau because it is a delay, is equals to summation of there are different channel parts. So one L1, L2, L3. The different lines are there, right? So there is a simple with alpha L T for different line. It is alpha the multiplicative factor multiplied by del of T minus tau A. Why here the del term is there? Anyway, the point is del. What is the Fourier transform of this del T? You know? It is nothing but 1. Okay. What is the Fourier transform of del of t minus tau I? It's nothing but e power minus tau I. Right. So if a channel is there, it is actually a phase shift. So this is showing phase shift. So since every channel tabs are showing the phase shift, so every channel tab is having one phase, second phase, third phase. So this tau L is a phase or the delay. You can call it as a delay also. The relative delay of tab I. That is a relative delay of tap I, where alpha t is a complex time varying gain with amplitude in a phase of tap L. So the frequency response is nothing but if you convert into this, the frequency response t will remain t. If you convert this to f, tau to f, it is same because it is scalar, and this is e power minus j omega t. So this is actually e power minus j omega tau. It is omega, j omega term should be there. So it is j omega 2 pi f is nothing but omega. So this is the frequency response. And you may wonder why you're not converting t to f. You are converting tau to f, you understand? Because tau is actually the relative delay of tap I. So the relation to coherence bandwidth, which is closely related to inverse RMS delay spread. Okay. Now there are significant difference between small scale and large scale fading. We have seen that, but still, what is the theoretical difference between those two? So large scale fading, which is basically through shadowing. Okay. Now you may ask what is shadowing? So shadowing is actually large scale fading is there through shadowing. There is actually slow variations due to path loss and obstacles, often modeled log normal, which is modeled as log normal. Okay. There's small scale fading, there's a multipath fading, where the rapid fluctuation, like if the distance is small, then the rapid fluctuation over distance comparable to wavelength. Like if you are comparable to wavelength, if you are doing this, and this distance, peak distance is lambda, as you know. And suppose we are going this distance. Okay, and if the frequency is high, obviously lambda becomes low. And since 5G is frequency band in the form of gigahertz and power 9. So if you convert lambda, lambda is equal to 3 into 10 to the power 8 divided by 10 to the power 9. So it is what? It is 0.3 meter. Can you imagine? 0.3 meter. If you go in that direction, if the fading is there, that is called small scale fading. Okay. So there modeled statistically where it is Rayleigh, Raytheon, Nakamami. Important scales are like Doppler spread, FD, which is FD, coherence time TC, which is TC. Sometimes in small scale fading, it's 1 by FD, and the coherence bandwidth is equivalent to 1 upon 5 tau sigma T. So here sigma T tau, which is sigma tau. Sigma tau is nothing but the variance. It's sigma square tau is variance of tapped delay. So this delay, as you say, this is a tau tapped delay, relative delay of tap I. If you model it and you get it, it is similar to 1 upon 5 C, tau T. So Rayleigh fading when it is applicable. So sometimes you may wonder how will we model different types of fading. So when the Rayleigh fading is applicable, the question is when it is applicable. So Rayleigh fading applies when there is no dominant line of sight component and the received signal is sum of many unresolved multipath components like central limit theorem is there. So if Rayleigh fading there when there is no line of sight component involved at all and the received signal is sum of many unresolved parts, then it is called Rayleigh fading. So let any complex number, for example, complex envelope is x is equals to j x are in phase components I plus xq, which is out a quadrature phase component where xi and xq is nothing but Gaussian and they are independent. Then the converse envelope, which is R, follows the Rayleigh distribution. So x is equals to j plus xq. So x mod is equals to R, which is equals to x and then I square plus xq square. And if both are Gaussian, then it becomes Rayleigh. Rayleigh PDF and CDM is like this. For PDF of envelope R. So it is called envelope because since the in phase component and out phase component, if it is like this, and if you're taking this, then it is called envelope in case of distribution. And so these are the PDF FR of R is equal to R by sigma square e power minus R square divided by 2 sigma square. And if you want it, since R component is involved, so like this, it will be looking like this. FR of R. And if you integrate it, then you'll get the CDF. And integration is from minus infinity to x, FR of R, and it is FR of R dr. Then you'll get this. So it is 1 minus e power minus R square divided 2 sigma square. Parameter relation is like E into R, E of R square is equal to 2 sigma square, which is average power, often denoted as sigma omega is equal to E power of R square, E of R square. Interpretation is like mode at R is equal to sigma, medium from CDF, R of med is equal to sigma root over 2 L into this median. And mode, how many times the frequency is, how many times that frequency is repeated is called mode. And mean, mode, median is the statistical parameters. So statistical moments of a Rayleigh distribution is E is expected value. So you may wonder what is the formula for expected value. So it is R fx of dx minus infinity to infinity R. E of R square is what? Minus infinity to infinity R square of x by fr of dr. Sorry, I'm writing x here. So this is what it is. Mean, which is expected envelope E of R is equals to sigma root over pi by 2. Second moment is power E of R square is equals to sigma square. Variance V of where of R is equal to 4 minus pi sigma square by 2. SNR relation instantaneous SNR. Sigma gamma is equals to R square by naught. Average SNR is nothing but, since it is average, so it is averaged over a particular interval. So if you average this over particular interval, it will become omega divided by n. So what is the difference between envelope versus power distribution? There's this question used to come in my mind when I was reading this wireless communications. So power is rho is equals to R square, which follows exponential distribution. If P of P is nothing but 1 upon omega e power minus rho by omega, where rho is greater than equal to 0. So if you integrate it, this is a convenient for outage and average being here. So this power, if you see R is what? Root over, sorry, mod of x it was, right? It is an envelope. Okay, and it was x of I plus x of q square. If you find an distribution of R square, then it becomes exponential distribution. That is a point. If you square it, then it will become exponential distribution. And for this, it just follows like this. And this is what it is useful for outage and BER probability. There are terms called level crossing rate and average wait duration. So level crossing rate, there are two important metrics. So they are important dynamic metrics for mobile channels. Since this course is all about the channels, how to model it, how to characterize it, how to validate it. So these are metrics for that. So LCR, which is level crossing rate, it's suppose it is level R, the average rate at which the envelope crosses that level in a positive direction is LCR. Similarly, there's a term called average fade duration. So at level R. So for these two, you are defining the level. So the average duration at which an envelope stays below R is that AFDR is equals to FR of R divided by LCR. So interpretation is like higher Doppler FD is equals to more rapid crossings and shorter fields. So we are defining two metrics and the Doppler frequencies. So how the Doppler was related? You remember the bandwidth, sorry, the R. Here I defined one term here. Yes, the coherence time was inversely proportional to FD. What does this mean? So what happens whenever we transmit any message, for example like this, to a channel, but every channel is having coherence bandwidth. Yeah, this is B. So if the input frequency Fn is less than B, then no frequency selective fading equal to or less. Similarly, if T, this is the input channel, input frequency, if it is greater than or equals to coherence TC, sorry, this is T input, like time duration of message signal is greater than or equals to TC, the same will happen. Okay. But if FD is high, right, then TC will be low. So if TC will be low, then in that case, message signal has to get lower upper bound, lower bond. In that case, it's very difficult for signal to transmit. So that's why the frequency Doppler spread significantly affects the frequency selective fading, and it causes also affect frequency selective fading. And why the frequency selective fading occurs? So it occurs because of mobility of two users. Okay, one user and two users. And the formula for this is this. Doppler spread and the channel time variance. So maximum Doppler shift is the relative frequency velocity of user divided by c into fc, which is equal to v by lambda. So where v is mobile speed, fc is the carrier frequency, lambda is the wavelength. The coherence time, which is equals to approximately 0. In case of jakes, 0.423 divided by ft. So channel is fast fading. If the simple duration, it was called greater than or equal to tc. Actually, if TS, the symbol duration is less than TC, then slow fading will happen. Okay, so in that case, there are two different types of fading. TS is greater than or equals to TC, fast fading. If TS equals less than or equals to TC, that's slow fading. Fading will happen, but it's really slow. So keep exact relation. If challenge changes significantly over symbol duration, inter-symbol variation will be there. Now, BER in AWGN versus fading, it is a conceptual difference. So AWGN, BER depends deterministically on SNR. In fading instantaneous SNR, gamma is random where the average BER is PB is equal to 0, integration from 0 to infinity PB of gamma, F gamma of gamma, D gamma. Where for Rayleigh it is this. This performs averaging over exponential PDF. The second thing is BER for BPSK and AWGN. So in that case, the AWGN instantaneous BER for coherent BPSKs, PB of gamma is equals to Q of root over 2 gamma is equals to 1 upon root over 2 pi. Integration from root over 2 gamma to infinity e power minus t square by 2 into dt. Use this integral to compute average BER in a fading. Average BER for BPSK over Rayleigh fading. So average BER BB is equals to 0 to infinity Q of root over 2 gamma multiplication of 1 by gamma bar e power minus gamma by gamma bar d gamma. So how it came? This is nothing but PDF. If you integrate this, you'll get this. Average BER. A closed form equation is this. A gamma bar is nothing but average SNR. So what we can interpret is this. Can you plot this? So for example, if you have high gamma bar, BB is equals to 1 upon 4 gamma bar, where diversity is of order 1. So compared to AWGN, you're having 1 by 2 e power minus gamma bar, which is exponential. It is over Rayleigh fading, it is over AWGN. So there is a significant difference between this. Like if you compare with the AWGN, it was equals to 1 upon 2 e power minus gamma. And there's a significant terms used, which is a diversity order and outage probability. So diversity order D from a high SNR behavior PB is proportional to gamma bar power minus T. And the Rayleigh single branch is D is equals to 1. So if it is a D is equals to 1, the diversity order is 1 and it's proportional to this. So outage probability for threshold gamma TH is nothing but if, as a name suggests, how will when the outage happens when it is less, the SNR is less than the threshold SNR, and that case is equals to 1 upon 1 minus e power minus gamma TH divided by gamma bar. So using this matrix for slow fading design is a link budget and a margin. Narrow band versus wide band fading. What is the difference? So narrow band is actually the flat fading where the band is very narrow, as the name suggests, and the channel gain is constant across the signal bandwidth, where W, the input frequency, is very, very less than BC. BC is the coherent bandwidth. So if it is less than that, then the signal is very constant, or the channel gain is very constant. So the all frequency components experience the same fading because since the signal is constant across this bandwidth, where the only phase and amplitude distortion will be there, then it is called narrowband fading. And on the other hand, wideband fading, which is frequency selective fading, is nothing but when the input signal bandwidth is greater than equals to BC, the signal spans multiple coherent bands and different frequency components fade differently, which is causing to ISI, intersymbol interference. Hmm. Why that happens? because the the channel bandwidth, suppose this, right? And the input signal frequency is this. Like you're telling, if it is less, then it will go easily, and all the signal is constant, and it will be a flat fading. And if the others are on hand, the signal is different, right? So the bandwidth is this only, so it will cause so much of fading here, or difference distortion is there. Then it is called frequency selective fading because it is caused through frequency selective. So actually, this lecture was completely on this theory and some formulas that you should know. So there's one term called power delay profile and RMS delay profile. So power delay profile, which is P of tau, is equals to nothing but expected value of mod of HT of tau square. So what does this mean? This is the average power per delay. So you're talking about delay, the tau. The tau distribution is what? It's nothing but exponential. So in that case, there's nothing but tau mean delay is this one, RMS delay is this one. Coherence bandwidth in that case, there is a rule of thumb in wireless communication is 1 upon 5 of tau sigma tau. So exponential, you may wonder Gaussian is also one of the exponential distribution. So, but in Gaussian is defined by two terms which is having mean and variance. So in that case, exponential is also one of the Gaussian distribution because Gaussian distribution is for 1 upon 2 root over 2 pi sigma square equal minus sigma exponent mu level 2 sigma square, right? So this sigma is was nothing but this sigma of tau. Giving you an example, suppose you are having two part channel, the frequency selectivity. In that case, h of tau is nothing but alpha naught delta tau plus alpha 1 delta tau minus tau 1. So you can say you're having two paths or the two tap delay components where the tap delay first is 0 and second is tau 1. The frequency response magnitude is nothing but magnitude of alpha naught if you convert into frequency Fourier transform, and it is alpha naught plus alpha 1 e power minus j 2 pi f tau 1. So if tau 1 is greater than Ts, suppose it is Ts, then strong frequency selectivity. Okay. And ISI will result. And it is less. Channel will appear first. Flat. Why that is the case? It is just opposite of this, right? BC. Because BC is inversely proportional to tau 1. It is actually a delay and it is inversely proportional. So the opposite symbol is used here, greater than. How would you calculate the BER in frequency selective channels? There are two approaches. Second is first is equalization, that is time domain or frequency domain to mitigate our ISI. Now you wonder what is equalization. You equalization in wireless communication. So name is this. It is the process mitigating channel induced distortions such as multipath fading, such as ISI, what frequency selective meaning? Right. So wireless communications are not ideal as we know. So equalizers are actually nothing but filters. That's what I wanted to say. Which can be linear, non-linear, adaptive, or fixed, which is designed to counteract these distortions so that the received signal resembles the transmitted one as closely as possible. So why ISI is needed to combat ISI, to improve bit error rate, to allow higher order modulation like QAM, OFDM, to enhance the spectral efficiency by enabling denser signal packing. So there are two types of equalization. First is linear equalization, which is allows you to use a linear filter to approximate the inverse of the channels. For example, zero forcing on minimum square mean square error. So I would like to give you some maths example of that. But again, there are some trade-offs. So in 2G, DFA and MLSE equalization in time domain is used, whereas in 3G, 4G, rake receivers and turbo equalization is used. 5G, 6G, people are telling OFDM with one tap per subscriber equalization is used, and advanced MIMO equalization used like MSC, MNSC, section, massive MIMO, linear equalization, like zero forcing and MMSC extended to multi-antenna case. So they are different. Like adaptive equalization is least mean square, recursive least square. This is a feedback equalization. Uses previous symbols instead to cancel ISI. Maximum likelihood, which is uses with Viterbi algorithm to find the most likely transmitter sequence. This is when feedback equalization uses linear filter to approximate the inverse of the channel. Zero forcing equalization, which cancel ISI completely but may amplify noise at the same time. So, but I'm giving you some examples. Uh, such one of the concept that it is required a lot. So, time domain DFE, which is nothing but time domain DFE, which is nothing but this is a feedback equalizer. Suppose you have a channel H is equals to 1.5, where channel is from the previous symbol, or the ISI from the previous symbol, BPSK, which is XN as we know. XN as we know, it is nothing but plus minus 1. Suppose the transmitter signal is plus 1, minus 1, plus 1, which is received, no noise, Yn is equals to X of n plus 0.5 X of n minus 1, assuming X of minus 1 is equals to 0. So how will the Yn will look like? So let us say y0, nothing but since it is 1, if we give 1 plus 0.5, 0.5 into 0, because it is 0 x minus 1, it is 1. Y of 1 is equals to minus 1 plus 0.5 into 1, 1 of 1, 0. So it is 1. So it is minus 0.5. Y of 2 is equals to 1 plus 0.5. This one is equals to 0.5. So if you say DFE with one feedback tab B1 is equals to 0.5 and forward gain of 1. So deciding this DFE with one feedback tab B1 is equals to 0.5 feed forward gain equals to 1, which is deciding x cap of m is equals to y of n minus 0.5 is cap of n minus 1. It is sigmoid function, signum of 1. So I'm deciding based on tab 1 and the feed forward gain of 1. 0.5 and feed forward gain of 1. Right from 0, its cap of 0 is equals to signum of 1 equals to 1, where n is equals to 1. Its cap of 1 is equals to signum of, what do you mean by signum? So signum function is this. Sorry, I didn't tell. It's minus 0.5 minus 0.5 into 1. It is signum of minus 1 is equals to minus 1. And it was 2. Its cap of 2 is equals to signum of 0.5 minus 0.5. Signum. So recovered signals are exactly is 1 plus 1 minus 1 plus 1. So how did you do? So in this case, we are having this is a feedback equalizer. So in that case, we are having feed forward tab of 0.5 and feed forward gain of 1. In that case, it is equal to this isn't based on this y of n minus 0.5 of x of n minus 1. In that case, it's perfectly perfect. And you're able to get the signals as plus 1, minus 1, and plus 1. So they recovered exactly plus 1, minus 1, plus 1. There are different equalizers, and OFDM one type equalization is there, which is zero forcing minimum mean square error, where for the subcarrier k, we are having y k is equals to h of k, x of k plus w of k. I'll give you that example also because it is very, very good. And one of the very good examples is there. Different type of equalization is first is OFDM, one tap equalization, which is zero forcing and MMC. And this is used in 5G, only in 5G. So rake receiver is also used in 4G, so that I will tell you about that later. So per sub k k is equals to y of k is equals to h of k into x of k plus w of k. So where h is channel matrix, xk is input matrix, and wk is the wk is nothing but the white noise. So here you are having x. And so for example, h is equals to 0.8 plus 0.68 plus 0.3 minus 0.4j plus 1 plus 0j, where y is equals to 0.4 plus 0.3j, 1.15 minus 0.2j, 0.9, and noise to signal ratio is nothing but n naught by px, right? Is 0.1. So zero forcing receiver, what it says it, zero forcing, where xk up of zero forcing is equals to yk divided by hk. Okay, so for different k is equals to 1, let's say, so it is nothing but 0.4 or 3j divided by 0.8 plus 0.6j, which is nothing but 0.5. You can calculate, it's one of the given example I'm taking. 0.15 minus 0.2j divided by 0.3 minus 0.4j is equals to 0.5. X is equals to 3. 0.9 divided by 1 is equals to 0.9. So MMSC says that MMSC. After that, X cap of MMSC, K is equals to HK of mod of HK square plus 0.1. 0.1 is a noise to signal ratio, and HK is that. So into YK. So in that case, H1 square is equals to 1, which equals to X cap 0.8 minus 0.68 divided by 1.1, 0.4 plus 0.3j. This 111, how? The one it will came. Xk of square 1 square plus 1. Similarly, we calculate it on S2 of square is equals to 0.25. S3 of square is equals to 1. And there is minimum least square error, which is also a Viterbi. This is a channel memory one. Channel is H is equals to 1.5 BPSKX, where ranging from 1 plus 1 minus 1. Y is equals to 1 minus 0.5. For example 1, the metric you can assume and you can calculate. There's an autocorrelation coefficient and the Doppler spectrum. Time autocorrelation of complex gain is nothing but expected value of h of t into h star of t plus tau. So what, like if you're calculating, if you have channel gain of like this, if you're calculating here multiplication with tau, this value multiply with this value, and then you're having this expected value for different time range, then it is for autocorrelation. And it is auto means if the signal is same. The cross means if the signal is one, another signal is like this. So you're having this and you're having this multiplying and then summing, multiplying and then summing, multiplying and summing. Then it is for cross correlation. For Class and a Jake's model, this uh, autocorrelation of delta t is nothing but J naught 2 pi f d into delta t. You can ignore this. Radiation varying again, it will have the line of sight component, and if the dominant line of sight exists, the envelope follows radiation distribution with k factor, and that is having this PDF. And the radiation distributes reduced to uh, Rayleigh for k is equal to 0. Nakagami in M mode and flexibility. So it is actually useful for fitting. So if M is actually a shape, omega is equals to E of R square covers many fading conditions. Rayleigh fading when M is equals to 1 or M greater than 1, it is less severe fading. Measurement based channel modeling at the steps. Collect channel impulse response using channel sounder or SDR, estimate PDP, mean delay, fit statistical distributions to envelope, estimate Doppler spread, channel estimation pilot design. So pilots, it inserts known symbols to estimate channel taps, trade-offs, pilot density versus overhead, whole pilots for fast feeding, high delay spread, pilot placement. We have this equalization techniques I told ZF. This is an feedback equalizer. We gave that. The OFDM single tap equalization per sub carrier. BAR improvement depends on residual ISA and channel estimation errors. Mitigation techniques, there are some ISI mitigation techniques also. So first is spatial diversity is MIMO. Frequency diversity, time diversity combining methods, maximum ratio combining. It weights by complex conjugate channel to maximize SNR. Selection combining it choose branch with as high as SNR. Equal gain combining it to equal weights for simpler implementation. MRC with L independent branches keeps diversity ordered. L average BER decays as gamma power minus L at high SNR. Choice of modulation and fading channel using the trade-offs. Highest efficiency versus robustness fading to fading. Some key considerations. The higher order cam, more sensitive to amplitude distortion, require higher SNR encoding. Critical efficiency versus robustness to fading. Higher order cam, more sensitive to amplitude distortion, requires higher SNR encoding. Phase shift key, which is a constant envelope to robust to nonlinear amplifier, was still affected by fading induced amplitude variation when combined with AWGM. Often combine adaptive modulation with link adaptation, rate control based on estimated SNR. Conditional BER. Adaptive modulation coding is actually deployed in 5G, and the principle is it will switch the modulation coding scheme according to instantaneous or channel quality. Threshold weight policy is like if it uses MCS, I if gamma ranges from gamma I to gamma I plus 1. This is nothing but the channel quality. And designing the thresholds to meet the target log error rate, which is considering the feedback delay. Outdated CSI leads to performance loss. Again, the practical design guidelines say like for low RMS, root mean square delay, the narrow band systems, it was simple and single antenna BPSK, QPSK with channel information often suffices. A wideband channel which is uses OMM plus cycle prefix longer than max X6 delay, allocate pilots per subcarrier. Use spatial diversity or frequency hopping to improve the reliability in harsh fading. Employ link adaptation and HRAQ to reach target throughput versus reliability trade-off. Question one. There's one question. Derive the PDF from the envelope then excuse this. So how will you derive? These are the steps which I have listed out. Join PDF in Cartesian coordinates. Mm. So first step is like join PDF in Cartesian coordinate is nothing but multiplication because in normal time domain, this is in frequency domain, f of t is equals to f1. Since it is a plus, right? So it is a plus. So join PDF, it's a convolution. So x, if you convolve it, this is what you'll get. Okay. Yes. So join PDF is nothing but minus infinity to infinity f of r f of r e power. Oh, this is what it is. So formula As we know, in order to define for probability, we know if it is greater than A, less than B, is equals to 1 upon A to B fx of dx. Right? So if we have two random variable x and y, suppose we have two random variable x and y, their joint probability distribution, how will it look like? It describes basically what it describes? It describes the probability behavior of both simultaneously. Probability behavior both simultaneously. Right. So if we talk about in case of discrete random variable, I'm telling you continuous only. So joint probability distribution function fx of x and y, x of y is greater than or equal to 0, which is minus infinity to infinity. F of x of y, x of y, xy, dx dy is equals to 1. Right. The probability of being in region A. So xy. So we need to integrate over f of x of f xy dx dy. So if we integrate over both, say x of I and x of q, then we are getting like this. So if you want to change to polar coordinates, x of I, which is in phase component, is equals to r cos theta. X of q, which is the quadrature component, is equals to r sin theta. The Jacobian of the transformation is nothing but del of xi x q divided by del of r theta, and which is nothing but r. So converting both, which is equals to r multiplied with Jacobian matrix. Jacobian nothing but you have to just j of x I x u divided by r theta, and that is r. Sorry, mod is r. Margin and PDF FR of R is, if you integrate over theta, it is FR of R. Similarly, if you're asked to calculate mean and variance of relay, how will you calculate? Mean simply by formula. Variance also by formula. Just take a look at this. So suppose we have next question. You are having average. The question is calculating the average BER for BPSQ over relay. So if we have PB is equals to 0 to infinity Q of 2 over 2 gamma F of gamma D of gamma for relay, the SNR PDF is this. What are the steps? How will you calculate? Use the identity for Q function 1 upon pi 0 to pi by 2 exponential of minus x squared by 2x sine squared theta d theta, where setting x is equals to root over 2 gamma. So q of 2 gamma is equals to 1 upon pi 0 to pi by 2 e power minus gamma divided by sine squared theta d theta. Interchanging the integrals and evaluating the inner exponential integral, you're having this. And finally getting PB is equals to 1 by 2. Multiplication is 1 minus root over gamma bar divided by 1 plus gamma bar. Moving to the next question, we have PDP with tau P of these values, compute the mean delay. How will you compute? These are the steps. So when it's bandwidth, just 1 upon 5 to Doppler shift. Ft is equals to V by lambda. Lambda you have to calculate and then we have to keep this value. Level crossing rate, keeping the formula with Ft is equals to 200 Hertz, sigma is equals to 1, R is equals to 1, compute LCR for relief envelope. LCR at R is equals to root over 2 pi Ft R by sigma e power minus R square divided by 2 sigma square. Keeping the evaluation you're getting, you can just cross verify by your calculations also. So why OFDM and wideband fading is used? There's a mathematical expression for this. Because the key idea is like OFDM splits the total bandwidth W into n narrow subcarriers of spacing delta is equals to W divided by n. Each subcarrier experiences approximately flat fading if delta F is very, very less than FD. So delta F is what? The initial frequency. If it is less than coherent bandwidth, then obviously you will be getting the flat uh, fading. Okay. You're getting fading, but that too, it's a flat. Okay. So mathematical effect is like this. Time domain convolution with channel h of t of tau becomes per subcarrier multiplication after FFT or DFT, and cyclic prefix ensures the circular convolution retains. So as we know, yk is equals to h of k, x of k plus n of k, where k ranges from 0 to n minus 1. So if CP length is greater than max excess delay, ISI is removed and per subcarrier equalization is single tap. So that's where the benefit of OFDM comes into the picture.
Any problematic equations are there, ma'am? Examples on this one?
What? Can you repeat?
Any problematic
Yes, yes.
examples are there?
Last year problems are there. Yes.
Hmm.
So there are some outage probabilities. So in this week, mostly the questions were from the formula based. Last year assignment questions also I saw is basically the formula based. Like for example, PR T is equals to 1.09. It's taken from last year. Shadowing is sigma is equals to 3 dB. Find the outage probability. So how will you calculate? So P out is equals to probability of 10 log 10 PR of T minus 10 log of minimum P minimum should be less than 0 because this is the threshold. So in that case, beta, which is the margin, is equals to 10 log 10 BR of D divided P minimum is nothing but 10 log 10, 1.091. So numerically, if you are solving, it is coming like this. So it's just P out is equals to Q of beta divided by sigma. Beta is equals to 0.379 divided by 3, and it is equals to Q of 0.1263. So this was one of the problematic example, and this was also one of the problematic example. In that case, the values were given. The user's speed V is equals to 60 kilometer per hour, and the carrier frequency is arbitrary. Then how will you calculate? Basically, based on this, because we know FD is equals to V by C into SC. But if it is having some inclination, which is theta, then it is called cos theta or the angle, which is the angle between the velocity and the line of sight vector. So in that case, the magnitude FD, in that case, what if the angle is given, how will you calculate? Magnitude of FD is equals to B by C, FC into cos of beta. If the user approaches BC, base station, the beta changes from 0 to pi by 2. And my question is like when FD is maximum. So since this formula states that this, right? So either the Doppler frequency is maximum when beta is 0 or 180 degree. So what can you say that either the user is moving towards the base station or away from the base station, it is maximum. And since it is magnitude, so cos of 180 degree is also plus 1. Basically, it is minus 1, but it is magnitude, it is plus 1. Right. So after crossing, beta moves from pi by 2 to pi, which increases again. So FD increases. So there were some two options. So in that case, FD increases or FD is maximum when the theta is 0 or it is 180 degree or one only or both. So answer was both. This question was very good. And I had another question, which is like user was moving on a circle center at base station. So how will you calculate this? How will you find it whether there will be Doppler shift or not? So the answer or the reasoning is since the velocity vector is actually tangential to circle, the line of sight vector which is from user to base station is radial. Okay, and it is tangent, 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 tangent. Okay. So the angle between the velocity and the propagation direction is 180 degree always. Radial, it is 180 degree. Right. So since cos beta is involved, so beta is 90 degree and beta to cos beta is 90 is 0. So in that case, there will be no Doppler shift if it is moving in a circle centered at base station or base station is residing in center. So this was also one of the very good reasoning questions, so I kept this. Also, this was also one of the uh, moderate question, which assumptions make relay feeding model valid. So one of the reason is like it should not be line of sight. Right. So all of the above. This second is correct. Second, third is like angle of arrival. Whenever the user is coming, it should be uniformly distributed. It is assumed like that. So it is basically for all the antenna which is leading to isotropic scattering. And one of the very important model is classical Jakes model. Also, many multipath components, if they add at receiver with random phases, which is leading to in phase or out phase component, which are Gaussian in nature, then it is called relay feeding because, as you know, R is equals to root over x square plus y square. Our x square is in phase component, y is in out phase component, or the quadrature component. And if you calculate, if you square this is the power density. That's it. And this was also one of the very good question, the numerical question, like yt is equals to x square of t, yt is equals to integration of t, yt is equals to sin t or convolution with the xt, and yt is equals to log 10 of xt. So one of my trick, if it is changing the order of any signal, then it is nonlinear in nature. Since the order is x of t and you're changing to square of t, so it is nonlinear in nature. Also, two properties should follow: superposition and linearity. Uh, Addition and superposition and scaling. Sorry, superposition and scaling. Two properties should follow. Superposition means if alpha x1 t plus beta x2 t should lead to alpha y1 t plus beta y2 t. This comes superposition plus scale. Scaling terms are there alpha beta and superposition is this. If xt tends to yt. Like if the system is xt is tending to yt, then alpha x1 t plus beta of x2 t should lead to alpha y1 t plus beta of y2 t. So this is the simple linearity problem. But this particular conditions will be followed if there is no change in the order. Since there is a change in the order, then non-linear. Since there is no change in the order, because integration, what it's doing is just a summation, right? You are having one value here, you are summing, then it is coming to integration. This is a graph, and if you want to sum it, this, then it will come like this, right? So that's why uniform distribution, if you integrate it, you will come the ramp function, right? Because if you are summing, it will come so like this. It will come like an answer. So it is a linear. What do you think? Sync T convolution with XT. Is it changing the order of XT? Is it changing? What do you think? If you're convolving any signal with XT, is it changing? No, right? Why? Because it is a signal function. This is a function which is convolving equally at every timestamp of any signal. Then it is not changing. You can check with this property also. This property will follow. Fourth, log 10 of xt minus 5. Obviously, this is non-linear because it is changing the order at all. So, which is linear. So, all are this is time variant distance. System is linear time variant. So, I was asking about linear, but time variance in the sense, uh, if you shift the input xt naught minus t minus t naught, it gives the output this, but sync is not changing. So, it is time variant. So, answer is this linear time variant. Yeah. Joint PDF of x and y. If x and y are Gaussian in nature, how we do calculate it? The derivation is there. I kept a derivation for you so that you will understand why derivation is important, and you should derive by yourself. The same analogy you have to convert to Jacobian format. If you want to convert one transformation to another transformation, in that case, you have to multiply by mod of Jacobian matrix. So here x, y are the polar coordinates. Uh, so if I convert to Cartesian and vice versa, so Jacobian for if you convert from r theta to x of y, it is nothing but r, where x equals to r cos theta, y is equals to r sin theta. And then multiply by this, you'll get that. Margin and PDF, if we integrate with another variable, we'll be getting the margin PDF. There are some derivations, like if you have transmitter at origin, which is reflecting wall at distance d from transmitter on the other side, and the receiver at distance r naught plus vt. Why receiver distance? Because vt is nothing but another distance where by a transmitter is moving with vehicle v. So which is moving away from transmitter with vehicle speed v. So what is a step-by-step derivation with the reflection? So you'll be getting this. The steps are this. Doppler spread among multipath components. This is also very interesting topic. You are having different paths from transmitter to receiver. Now, how will you get the Doppler spread across different paths? So Doppler of direct path, which is FD1, is equals to V by C FC cos beta 1. Right? We know. Now, for the reflected path, for the angle of arrival relative to velocity is same as magnitude in this symmetry. So, angle of arrival for beta 2, beta 1 is same because mod of cos beta 1, cos beta 2 is same. So, it is same. So, it is actually FD1 is equals to FD2 in magnitude and Doppler spread. It is equals to 0. The question is not clear. complete here. Delay spread in two-path scenario. So minimum propagation time, which is a direct path, is equals to R naught by C. The maximum propagation time of the reflected path is 2D plus R naught by C. And if you calculate the difference between these two, R naught is their initial distance, right? It's 2D. The question was coherence time versus Doppler square. It is inversely proportional as we know. So coherence bandwidth versus delay spread. Like RMS delay spread sigma tau measures multipath spread in time. Coherence bandwidth B of C roughly satisfy B of C is equals to 1 by 5 tau T, which is the rule of thumb. So larger delay spread equals to coherence inversely proportional. Same question. Ah, there's also another theoretical question asked last year is like best option in GSM to prevent the outage from fade. It can be forward direction error coding, frequency hopping, handoff, or stop transmission. So in general, the GSM, which is a 2G, it uses frequency hopping because frequency hopping moves bursts across carrier frequencies. Deep fades are frequency selective and unlikely to affect all the hops, which is frequency diversity. And FEC helps but may not require them. Deep narrowband fades and of helps mobility but not instantaneous frequency certificates. What if a set of OFDM subcarriers are in fade? What will be the best option? Option was to avoid subcarriers, to do frequency hopping, to do forward direction coding, or to avoid none. So what I feel is like we have to not transmit the data on those subcarriers or resource allocation manually, because a subcarrier is known to be in defade, which carries the actual information, right? Scheduler can avoid allocating data to them, but apply bit loading to reduce rate. Frequency hopping or the diversity techniques could also help, but immediate practical step is to avoid the subcarriers. I will directly avoid that subcarriers. Marginal PDM. Hmm. Which curves? So there was one different types of curves were given. So I plotted which curve approximates only path loss. So if we have receive power and the distance, how the path loss actually varies if it is in dB. So as you know, dB in dB, everything is sum, right? Everything is sum. So it is was direct this path because a path loss is more deterministic decay without any fluctuations. It is in dB, that's why. And what if we have shadowing? Then it is like this slow, long, normal variation across path loss. It is the red curve. Margin for 2% outage, how will you calculate? So P out is equals to Q of beta by sigma is equals to 0.02. Sigma is equals to 3 dB. Z is equals to this one. Beta is equals to questions for two. I think enough for this class. So for week 4, what I will suggest is please go through the actual formulas. Uh, you have to keep, uh, you have to learn those formulas, and for the for for deriving you should derive by yourself, then only you will be able to derive. There are steps that you can find in my notes, in my slides, but what I will suggest is please try by yourself also. Thank you so much for joining. I think I will end the class today. I'm not feeling well. uh, if you have any doubt, you can just let me know. You can reach out to me at my email ID. You can reach out to me through my YouTube account, through my LinkedIn account. I'm active there. I will reply. And also there are three TAs. All are teaching similar or same sort of question. If you are liking any one of the TA or any TA, please do give the feedback. And that's it from my side. Thank you so much.
Thank you, ma'am.
Yeah, thank you, Gish.
Thank you, madam.
Thank you, Shita.
Thank you, ma'am.
Thank you.